Good day, everyone. Today, we're going to continue on our discussion on two-level fractional factorial design, which is Unit 2-4. So let's start off with an example of a resolution 5 2 to the 5 minus 1 design, which is an example on how to use factorial design in process improvement. Suppose that you have 5 factors in a manufacturing process for an integrated circuit that you want to investigate in a 2 to the 5 minus 1 design with the objective of improving the process yield. Now, the 5 factors are A, denoted as A, aperture setting, with levels small and large. And then you have exposure time, denoted as B, with levels 20% below nominal and 20% above nominal. You have develop time, denoted as C, with levels 30 and 45 seconds. You have mask dimension, denoted as D, I should say, with levels small and large. And finally, you have etch time, denoted as E, at levels 14.5 and 15.5 minutes. So first, we construct the basic design. Okay, so let me show you with this spreadsheet. All right, so as you can see here, we start with a basic design having 2 to the 5 minus 1 full factorial. Okay, or basing on a 2 to the 5 minus 1 factorial. So that's 2 to the 4. So we have the factors A, B, C, and D. Okay, and remember that to derive E, we basically equate it to the highest interaction, okay, of the 2 to the 5 minus 1 factorial design, and that would be A, B, C, D. And we derive the signs under this column by multiplying the signs under A, B, C, and D. With this, we then know that the defining relation is A, B, C, D, E. Okay, I equals A, B, C, D, E. All right, so with the 2 to the 4 full factorial design, we would have 16 total combinations. Okay, and these are the signs for each of the factors. And multiplying those with each other, we get the signs for the column under E. Okay? Now, looking at the signs, we can then identify the treatment combination. So, for example, okay, we have -1, -1, -1, -1. And if we multiply all of that under E, we would have +1. Okay? So negative signs under each of the main factors, okay, from the basic design, and then you have a positive sign under E. Therefore, if we interpret this in terms of a treatment combination of a 2 to the 5 factorial design, we would have a combination of E, which means that at E, we have a high level. With the treatment combination E, okay, we have a high level of the factor E and low levels for all the other factors. Same is true with A here. You can see that only factor A has a positive sign while the rest have negative, okay, which means that the rest have a low level and A here is high level. Therefore, the treatment combination here is small a, and so on. So from here, you can now identify the treatment combinations to run in the experiment. And again, remember to run the combinations in random manner, okay, when running the experiment. Okay, so say that from the experiment, you were able to observe the following process yields for each of these treatment combinations. So you have 8, 9, 34, and so on, respectively, for each of these combinations. Okay. What's next? So now we proceed with the estimation of the effects. Okay? And we know that from the fractional factorial, okay, in brackets here, A, B, C, D, E, and the two-level interactions, okay, we know that they're actually estimates of the combination of the main factor, okay, and an alias, for example, for A. Okay. So A in brackets is actually A plus B, C, D, E. Okay. B in brackets is B plus A, C, D, E. Okay, and how did we derive BCDE here? Okay, we basically multiply A by the defining relation, which is ABCDE. Okay, and if you do that, you get BCDE, and so on. Okay, so each of these are actually equal to the aliases corresponding to them, right? So now let's proceed to the analysis. Okay, so first we get the contrast. From the table of plus and minuses, we can obtain the contrast of each of these factors or effects. Okay, so for example, for A, by using the signs, okay, that we have in the table of plus and minuses, okay, and getting the sum product of that, I just made it -1 and +1, okay, so that I can easily manipulate the vectors, okay, in this spreadsheet and actually do a sum product, okay, between the minus and plus ones here, okay, and the observation, okay, under process yield. So 89 here, okay, is the contrast for factor A. Contrast for factor A in brackets, of course. And I just do the same thing for the rest, no? So it's sum product of this column and the observation column. Now, after getting the contrasts, okay, to get the effect, I just multiply the contrast by 1/8, okay, because we have a 2 to the 4 design here. So from there, okay, you can see that we can also derive the regression coefficient here. And we know that the regression coefficient would just be 1/2 of the effect estimate, okay, from previous discussions. And then you can also have your sum of squares, okay, and the sum of squares is basically the contrast square divided by 16. Okay. Now let's look further on the effects column. You can see that factors A, B, C, and the interaction between A and B seem to have the highest, or the largest effect, okay, in comparison with the effect estimates of the other effects. Okay. Okay, and we can verify that from a normal probability plot. As you can see, A, C, B, and AB are far from the normal line. And this would lead us to conclude that A, B, C, and AB are significant. But take note that these are in brackets, all right, because we derived it from the 1/2 fraction. Okay. However, knowing that A, B, and C are the main effects that are significant, and then AB, AB here, okay, is also significant. Let's go back to the aliases. So, what would be the alias of A? That would be a four-factor interaction. Alias of P is also a four-factor interaction. Alias of C, same. Alias of AB is a three-factor interaction, and we can assume, okay, that the high-order interactions are negligible. So it would be safe to conclude that A, B, C, and AB here are, without the brackets, okay, are significant. Okay, now from that, okay, if we summarize the ANOVA table for our model, okay, only including the significant effects, okay, we can see that the sum of squares, if we add the sum of squares of A, B, C, and AB, okay, that would be 5,747.25. That divided by the total sum of squares, it gives us more than 99%, which could be translated to an interpretation which basically means that A, B, C, and AB can explain over 99% of the variation of the variability of the response variable, which is the yield. Okay, so in other words, the model can explain over 99% of the variability in the process. So this sounds to be a really, really good model. Okay, now let's investigate further using a graph. So you can see here the graph of A and factors A and B. Okay, and you can verify with this graphical investigation that there is indeed an A-B interaction and that the yield is higher when both A and B are at the high level, as you can see here. Okay. Now, looking further at some graphs, you can also see here that the yield is highest when A, B, and C, okay, are at their highest, are at their high levels. As you can see here, we have 61.5 compared to these numbers here below when B is at a low level, or here, okay, when C has a low level, or here when A has a low level. Now we also have to do, again, as usual, residual analysis. And as you can see, this normal probability, the residual graph, as well as the residuals versus the predicted yield graph seem to be satisfactory. Okay. Now you can also take note that the 2 to the 5 design can actually collapse into a 2 to the 3 design with 2 replicates in any of the factors. No? Okay, now let's proceed to sequences of fractional factorials. If you remember at the start of our discussion, we talked about 3 principles or 3 key ideas that guide fractional factorial experimentation. Okay, and one of which is sequential experimentation. And from Montgomery, it states that it is possible to combine the runs of 2 or more fractional factorials to construct sequentially a larger design to estimate the factor effects and interactions of interest. Okay. And here are some motivations, okay, for follow-up experimentation after initial fractional factorial design. So one could be that you intend to perform 1 or more confirmation runs to verify conclusions from the initial experiment. And you might also be interested in adding more runs to clarify the results. Okay, so for example, to resolve aliasing, no? And then you can also change the scale on 1 or more factors. Another motivation would be to add runs to allow modeling additional terms, such as quadratic effects needed because of curvature. You may also drop or add factors. You may replicate some runs to improve precision of estimation or to verify that runs were made correctly. And you may also move to a new experimental region that is more likely to contain desirable response variables. Okay, so let's go back to the filtration rate of a chemical product example to illustrate sequential experimentation. No? So you remember this experiment, right? And these were the effect estimates. Okay, these were the effect estimate from the 1/2 fraction of the experiment. Okay, we found that AC, and AD, okay, were the major effects. Okay, we assumed that higher order interactions are likely negligible. Therefore, AC and B likely have large effects, and consequently, AC and AD are also likely the major effects, and BD and BC are likely negligible. Also, by virtue of weak heredity, AB may not be uh, uh, large, all right? Now, what if we want to verify whether AC and AD indeed are significant? Okay, so what we can do is do a sequential run. Okay, so we run the other half of the fractional factorial. And of course, since we already ran the principal fraction, I should say, then we can then sequentially run the alternate fraction, which will have the defining relation I equals negative ABCD. Okay, so remember that this is how we constructed the principal fraction. We made the 2 to the 3 full factorial as our basic design and had D equal to the highest order interaction for a 2 to the 3 design, which means we would have ABC, and then the defining relation is ABCD. And with that, we obtained the following treatment combinations. Now, to get the complementary fraction, okay, we basically negate, okay, the signs under the last column, which is under D, all right? And so our defining relation here is negative ABCD. And we would find that the treatment combinations are the following: D, A, B, ABD, C, ACD, BCD, and ABC. Given those treatment combinations for the complementary fraction, let's now continue with the analysis of this experiment. Now, these are the filtration rates corresponding to those treatment combinations. Note that these values were obtained from the data from the previous example. But of course, again, take note that you have to run you have to perform the runs randomly, okay? And this is just for the sake of illustration. Okay? So in real life, you're supposed to run these treatment combinations randomly, and then you would get data for each of these treatment combinations. Okay, now given these values for each of these treatment combinations, we can now proceed with the analysis of the alternate fraction. So after you are done with the analysis of the complementary fraction, you can combine that with the results from the principal fraction to be able to extract the actual estimates for the factors and the interactions. So for example, for A, you basically get the sum of the estimate of A from the principal fraction and that from the complementary fraction and divide that by 2. And their aliases, okay, their aliases, the effect estimates for their aliases can be obtained by getting 1/2 of the difference of their estimate from the principal fraction and minus that from the complementary fraction. Okay, so to make that clearer, let's look at this spreadsheet. Okay, so say we got the following effect estimates for A prime, okay? And previously we got this effect estimate for A. So to get the actual effect estimate for A, then we just get the sum of 19 and 24.25 and then divide that by 2. Now, since BCD is the alias of A, we get its actual effect estimate by getting the difference between A, okay, so 19, minus A prime. Okay, so A minus A prime divided by 2, okay, and so on. So as you know, okay, you have to know which what are the aliases for each of the factors and interactions, okay, so that you are able to determine the appropriate formula that you can use to determine the effect estimate for each after running the complementary fraction. Okay. Now, as you can see in this summary of the effect estimates, we can then verify that A, C, and D are the main factors that are important, and that AC and AD, okay, are the interactions that are important. Okay, so BC, okay, and we can now rule out the idea that BC and BD are also important. Okay, so we can then conclude that our initial or our preliminary conclusion that AC and AD are the interactions that are important is true. Okay. Of course, with the key idea of sequential experiments, okay, we can also relate this to the concept of confirmation experiments. And you can perform confirmation experiments by running sequential experiments or running the alternate fraction. Okay? You can also compare the predicted versus the observed responses at the point of interest. And to do this, first you use the model equation to predict the response at the point of interest in the design space. Okay? And this should be a treatment combination that was not used in deriving the model. And then you run the treatment combination, and then you compare the predicted versus the observed values. Okay, so let's take a look at this example. So going back to the previous example, this would be the corresponding model equation. Okay? And we use this model equation to predict a response at the point of interest. So say, for example, that the point of interest is at C at the high level of A, low level of C, okay, high level of D, and high level of D. Okay, so then we substitute either 1 or -1 to the excess, okay? And recall that we are interested in this point because it is key to solving the problem in this example. Okay. So as you can see here, the predicted value would be 100.25. Now, say that the treatment combination is run, okay, from the example data. The observed response is 104, for example. So 104 and 100.25 are very similar. Therefore, we can conclude from this that our initial conclusions could be correct. Now let us proceed to 1/4 fraction of the 2 to the p design. Okay, so the motivation behind the 1/4 fraction of the 2 to the p design is very familiar to you. So say you have moderately large number of factors. You would have to perform so many runs, right? And therefore, smaller fractions of the full 2 to the p design would be useful. And of course, we already talked about 1/2 a fraction. And what if we need even smaller number of runs? Then we can resort to the 1/4 fraction of the 2 to the p design. So for example, instead of so in notation, no, instead of 2 to the k runs or a 2 to the k full factorial, you could run a 2 to the k minus 2 fractional factorial. Okay, and that would also mean that your total number of runs, they would be 2 to the k minus 2 instead of 2 to the k. Okay, so as a specific example, 1/4 fraction design of an experiment investigating 6 factors with 2 levels would require 2 to the 4. So that's 2 to the 6 minus 2, which is just 16 runs instead of the 64 runs came from the full factorial design. You know, so how do you construct the 1/4 fraction? It's very similar to what we've discussed already in under constructing 1/2 fraction of a 2 to the p design. So the first step is again formulate the basic design. Okay, so that is you run for a full 2 to the k minus 2 design. So in the case of the 1/2 fraction, we ran the basic design would be running a full 2 to the k minus 1 design. So as you can see now, p here is equal to 2. Okay, after formulating the basic design, you can now add the last two factors of the full design using two chosen generating relations. So we denote them as I equals P and I equals Q. P and Q are interactions of the first k minus 2 factors, right? Now, the principal fraction, okay, the principal fraction, there should be an S there. The principal fraction is that 1/4 where both P and Q are positive. Now, there would be three alternate fractions here, and alternate fractions are where either P or Q are negative or both are negative. Let's also define the complete defining relation. Okay, so for the 1/4 fraction of the 2 to the k design, the complete defining relation is I equals P equals Q, and there's a third expression which is basically the generalized interaction of P and Q. So the complete defining relation is I equals P equals Q equals PQ, and in the language of factorial design, PQ and PQ are words. Now, next is how do we determine the aliases in a 1/4 fraction? So you basically multiply the effect by each word in the defining relation. Okay? Therefore, each effect would have three aliases. So for example, for a 2 to the 6 minus 2 design, okay, the generating relations could be I equals ABCE and I equals BCDF. So our P and Q here are ABCE and BCDF. Okay? And the generalized interaction would be for the generalized interaction for ABCE and BCDEF would be ADEF. Okay? Therefore, the complete defining relation would then be I equals ABCE equals BCDF equals ADEF. Now, this results in resolution 4 design, which means that the main effects are aliased with 3 and 5-factor interactions, and then the 2-factor interactions are aliased with each other and with high-order interactions. With this, you avoid the problem of having aliases that might be of interest, and those effects that are probably of interest are the main effects and the lower level, the lower order interactions. Okay, so for your personal exercise, I want you to verify this. Okay, this claim that the results in this design would be a resolution 4 design. Okay. Again, we would like to emphasize that the generator should be chosen such that important effects are not aliased with each other. So we don't want the low order interactions to be aliased with each other, basically. Okay. Another exercise for you. Okay. If you might want to pause the video right now and answer each of these questions. Okay, so I'm still under construction of the 1/4 fraction. What factors would constitute the basic design of a 2 to the 6 minus 2 fractional factorial with generating relation I equals ABCE and I equals BCDF? Okay, and then how many runs would there be? Next, what would the signs on the last two columns be? And then what is the principal fraction and what are the alternate fractions? Okay, so you might want to pause the video right now and answer the following questions. All right, so now let's continue with the lecture, okay, and let's tackle the topic of a projection in a 1/4 fractional factorial. So in general, any 2 to the k minus 2 design can be collapsed into either a full factorial design or a fractional factorial in some subset of r is less than or equal to k minus 2. So for example, if you have a resolution for 2 to the 6 minus 2 design with complete defining relation I equals ABCE equals BCDEF equals ADEF, okay, this would project into either a single replicate of a 2 to the 4 full factorial design in any subset of 4 factors, or 2 replicates of a 2 to the 4 minus 1 factor, so it should be superscript, okay, of a 2 to the 4 minus 1 in factors A, B, C, E, BCDF, and ABF, and so on. Okay, now let's look at this example. Okay. So this is an injection molding process improvement example, and we will illustrate the use of 1/4 fractional factorial design with this example. Okay, so and this example is from Design and Analysis of Experiments by Montgomery. So parts manufactured in an injection molding process are showing excessive shrinkage. This is causing problems in assembly operations downstream from the injection molding area. A quality improvement team has decided to use a design experiment to study the injection molding process so that shrinkage can be reduced. The team decides to investigate 6 factors, namely mold temperature, denoted as A, screw speed, denoted as B, holding time, denoted as C, cycle time, denoted as D, gate size, denoted as E, and holding pressure, denoted as F. And each of these factors are at 2 levels with the objective of learning, okay, and the objective is to learn how each factor affects shrinkage and also something about how the factors interact. Okay, so that's a lot of factors. No? 1, 2, 3, 4, 5, 6 factors. Okay, and if you run the full factorial design, that would entail 64 runs, okay, for each replicate. Say that the team can only perform 16 runs, right? So it would be logical to use, or it would be reasonable to use a 1/4 fractional factorial design. Okay? And so the first step is for us to construct the 1/4 fraction, and that starts with the basic design. Okay, so since we have 6 factors, okay, the basic design would be constituted by the first k minus 2 factors. So that would be the first 4 factors. That's why you can see here A, B, C, D. Okay, and the basic design is corresponds to a therefore corresponds to a 2 to the 4 full factorial design. Right, so there would be 16 runs in that 2 to the 4 design. Okay, and these are the corresponding plus and minuses for each of these runs. Now, to construct the 1/4 fraction for our 2 to the 6 minus 2 design, we add the columns E and F, okay, the columns for E and F, and say that we say that we choose A, B, C, E, and B, C, D, F as the generators. Okay, then E here would be equal to A, B, C, and F here would be equal to B, C, D. Okay, and to get the signs for column E, we just multiply the signs under A, B, and C, and then for F, we just multiply the signs for B, C, and D. Okay, so again, this is the basic design, and then as I mentioned earlier, E would just be equal to A times B, okay, A times B times C, and then F would just be equal to B times C times D. Right? The cells highlighted in pink are basically positive signs, so plus sign. Okay, now given that, we can now identify the treatment combinations to run under the 1/4 fraction of the full factorial. Okay, and those would be, okay, given these plus and minus signs, those would be 1, AE, BEF, ABF, and so on. Okay. All right. So we have 16 combinations here. So now we know the treatment combinations for the principal fraction. And I say that this is the principal fraction because P and Q here are positive. Okay. So now say that these are the observed shrinkages that the team obtained for each of these treatment combinations. Okay, so 6, 10, 32, and so on. These values are also shown in DAE by Montgomery. Now, given those values, observed values, we can then now proceed to analyze the 1/4 fraction, which in particular is the principal fraction in this case, right? So first we can calculate for the contrast and then the effect, and then we can also calculate for the regression coefficient and the sum of squares, right? And we know that in the A here, okay, in brackets, is actually A plus its aliases, okay? And as I mentioned earlier, A here would have 3 aliases. So before we proceed with the analysis or the estimation of the effects, let's first look at the aliases. Okay? All right, so remember that the complete defining relation here is ABCE, BCDF, and ADEF. Okay, so for A, the aliases of A are BCE, okay, because that's A times ABCE, that would be BCE. A times BCDF, that would be ABCDF, and then A times ADEF, that would be BFE. And you just do the same thing to get the aliases for each of these main factors and interactions. Recall that the complete defining relation for this example is I equals ABCE, BCDF, and ADEF. And so to get the alias of A, we multiply it by each of these generators. So A times ABCE equals BCE, A times BCDF equals ABCDF, and then A times ADEF is DEEF. Okay, so that should be DEF. Then you just do the same thing for the factors and the interactions to get the aliases. And there are 3 aliases in this case. Note here that I indicated in bold the main factors and the 2-factor interactions. Because as you will see later on in our analysis, we will only focus on the main factors and the 2-factor interactions because we will call upon the assumption that high-order interactions are considered negligible. Okay? So now we proceed to the estimation of the effects. And the effect can be computed as contrast divided by 8, okay? 8 in this case. And the contrast is basically the sum product of the plus and minus ones under each factor and interaction times the observed the vector of the observed values. Okay, so we get these values, okay, for each of the factors and interactions, and then we just divide those, okay, by 8 to get the effect, right? And then for the regression coefficient, remember that we have to divide the effect estimate by 2. And then the sum of squares is just contrast square divided by 16 in this case. All right. And based on these values, we can see that A, B, and then AB plus CE, effectively, okay, have large effects, okay, relative to the others, as you can see. Now, again, you might be wondering why this, okay, so these are the actual variables. Now, you might be wondering why it's just A. Again, as I mentioned earlier, we are considering the high order interactions as negligible. So bracket A here would just be considered as also equal to A. And then AB, bracket AB here is considered equal to AB plus CE because AB has the aliases CE, CDF, and DEF, and we consider CDF and DEF as negligible. Okay, so we find AB and AB to be the large effects. And we can verify that with a normal probability plot. Okay, you can see here AB and AB as the large effects. And if we look at the graph okay, for A and B, in the interaction of A and B, we can see that at low level of B, the shrinkage is actually not sensitive to mold temperature, right? As you can see here, it's almost horizontal. However, at high level of B, okay, the shrinkage is sensitive to mold temperature. Okay? Therefore, we can infer from this graph that the process is sensitive to mold temperature at high screw speed. B here is screw speed, right? Now, based on our initial analysis, the best thing to do then is to set the mold temperature, okay, and the screw speed at low level, okay, to minimize the shrinkage. We can derive the regression equation for our design, and that would be y hat equals beta naught hat plus beta 1 hat x1 plus beta 2 hat x2 plus beta 1 2 hat x1 x2. And beta naught here is just the average of the observations. X1 and X2 are coded variables for factor A and factor B, which are mold temperature and screw speed. Okay? And beta 1 hat and beta 2 hat are the regression coefficients for A and B, and then beta 1, 2 hat is a regression coefficient for the interaction between A and B. And we already obtained these values as I showed you in the previous table. Okay? And these are the values. Okay? Now, of course, again, we have to check whether the model is adequate and that assumptions are not violated. Residual being observed minus predicted, okay, that it is very close to the normal probability line. Okay, so the residuals are close to the normal probability line, which means that the normality assumption is not violated here. Okay, it is also interesting to determine whether a factor, okay, can affect part-to-part variability in shrinkage. Okay, and if you plot the residuals versus each of the factors, okay, you will see that um, for factor C, which is the holding time, it seems that the residuals have wider spread under high holding time relative to low holding time. And if we and this indicates that there could be a dispersion effect, okay, or variability effect related to holding time C. All right, and we can verify this by looking at uh, the parameter f for holding time C, which is equal to ln of s squared, okay, for I plus divided by s squared for I minus, where I plus is basically high level of C, and then I minus is low level of C. Okay, so this would be equal to 2.5, and compared to the other to the values of the other corresponding to the other factors, okay, this is relatively high, and therefore the dispersion or variability effect related to factor C is real. Okay? And based on this, it would be more desirable to have, of course, lower variability, part-to-part variability in shrinkage. Therefore, we would prefer the holding time to be at low level. Okay? Now, verifying, okay, as you can see, this is the normal probability plot of the values for F. C is much farther, no, from the rest, okay, and from the normal probability line. So FC is relatively large. Therefore, the dispersion effect, variability effect is, as we said, real. No. Now, based on this cube, okay, these are the corresponding conclusions that we can derive. Set the screw speed at low and set the holding time at low. Why do we want to set the screw speed at low? If you compare the bottom plane versus the upper plane, you will see that the values for y bar, okay, are actually lower. Okay? The values for y bar are lower, which means that regardless of the temperature, mold temperature, you actually have lower shrinkage. Alright? Now, why do we want to set the holding time at low as well? We compare the range values uh, when the holding time is at low and the holding time is high. You can see that the ranges are much higher, okay, when the holding time is high. Okay? And we don't want that. Therefore, to optimize the process, okay, or to improve the process at least, we set the screw speed at low and set the holding time at low. Now let's proceed to the general 2 to the k minus p fractional factorial design. Okay, so a 2 to the k minus p fractional factorial design is basically a 2 to the k fractional factorial design containing 2 to the k minus p runs. And it is a 1 over 2 to the p fraction of the full 2 to the k design. So for example, if your p is equal to 1, okay, that would mean that it is a 1/2 fraction of the full 2 to the k design. If your p is equal to 2, okay, then you have a 1/4, a fraction of the full 2 to the k design, and so on. Now, some notes on alias generation. So you already know the general process of constructing the fraction of the full factorial, as we've shown in 1/2 fraction and 1/4 fraction. And we note that in alias generation, okay, we basically multiply each effect column by the defining relation, and the p generators and this would be the p generators and their generalized interactions. Okay, and then remember also not to choose a generator that would make major effects alias with each other. And at large k, the high order interactions can be assumed negligible, and this would simplify the alias structure. Now, in choosing the P generators, you have to aim for the following. One, that you will be able to generate the highest possible resolution, and that you would have less extensive aliasing, and you would minimize aberration design. And what does this mean? That you would have minimum number of main effects alias with interactions of order r minus 1, minimum number of two-factor interactions alias with interactions of uh, order r minus 2, and so forth. Okay. Now, so for k is less than or equal to 15, I direct you to see table 8.14 in appendix table 10 of the Design and Analysis of Experiment by Montgomery 2012 for suggested generators and alias relationships respectively. Now, for the analysis of 2 to the k minus p fractional factorials is actually pretty simple. To estimate the effect I, this is just equal to 2 times the contrast I divided by n, which simplifies to contrast I divided by n over 2, where n is equal to 2 raised to k minus p. So, for example, um, if you have a 2 to the 6 minus 2, okay, 2 to the 6 minus 2 design, that would mean that your n is equal to 2 to the 4, which is equal to 16. Okay. Now we talk about blocking in fractional factorials. So let's first talk about the motivation for blocking in fractional factorials. Okay. Now, runs under each fraction, there could be situations where runs under each fraction are still too many to be made under homogeneous conditions. And if you have this situation, then fractional factorials may be confounded in blocks. And for this use, I direct you to Appendix Table 10 of DIE by Montgomery 2012 for the recommended blocking arrangements, okay, um, corresponding to the designs shown in Table 8.14. Okay, now let's look at an example to illustrate, no, blocking in fractional factorials. So say you have a 5-axis CNC machine that is used to produce an impeller for a jet turbine engine. The blade profiles are an important quality characteristic. Specifically, the deviation of the blade profile from the profile specified on the engineering drawing is of interest. An experiment is run to determine which machine parameters affect profile deviation. And the 8 factors selected for the design are as follows. So you have A, which is the x-axis shift, A, B, which is the y-axis shift, C is the z-axis shift, D is equal to the tool supplier, E is equal to the alpha axis shift, F is the spindle speed in percent, G is the fixture height, and then H is the feed rate. And these are the levels investigated in this experiment. Now, one test blade on each part is selected for inspection. The profile deviation is measured using a coordinate measuring machine, and the standard deviation of the difference between the actual profile and the specified profile is used as the response variable. The machine has 4 spindles. Because there may be differences in the spindles, the process engineers feel that the spindles should be treated as blocks. Okay? Now, the engineers feel confident that 3-factor and higher interactions are not too important, but they are reluctant to ignore the 2-factor interactions. Referring to Table 8.14, so these are the recommended designs for each of these for the number of factors k. In our case, we have k equals 8. And for k equals 8, these are the fractional factorial designs that are recommended. Okay, so you have 2 to the 4, 2 to the 8 minus 4 resolution for design. And with that, you would have 16 runs. Okay, this one would have 32 runs, this one would have 64 runs, and these are the recommended design generators. Now, if you look at Appendix Table 10, in DAE by Montgomery, you would have the aliases corresponding to each of these designs. Okay? And based on that table, you would find that in a 16-run design, okay, there will be fairly extensive aliasing of 2-factor interactions. Running the design in 4 blocks would require confounding 4 2-factor interactions with blocks. And then if you look at the 32-run design, you will find that it would only confound 1. It is more desirable to adopt this 32-run design, the resolution for 2 to the 8 minus 3 design, okay, because we don't want to sacrifice the information regarding the 2-factor interactions. Based on the recommended design, these are going to be your generating relations. Okay, so you would have ABCF, ABDG, BCDEH, and BCDEH. Okay, with that, you would be able to generate column F, G, and H by multiplying. For F, you would just multiply columns A, B, and C. For G, just multiply A, B, and D, and then for H, just multiply B, C, D, and E. And these are the recommended blocks for the different runs. Now, suppose that these are the, and this is suppose that this is the actual run order, okay, and these are the observed standard deviations, okay, in cubic inch. You can, as usual, you can calculate for the contrast, the effects, the regression coefficient, and the sums of squares. And if you plot the effects in a normal probability plot, you will see that factors A and B are large, have large effects, and AD also has a large effect. Okay, and now by virtue of the hierarchy principle, we have to include also factor D, okay, because of the interaction between AD here. Okay, and now if we look at the ANOVA, okay, summarizing the ANOVA for the different sources of variation, only including those that have large effects, namely A, B, D, AD, then we would have this ANOVA. Okay, and of course we have the added row for blocks here.
Okay, and as you can see, the factors A, B, and D and the interaction have very low p-value. Okay, now if we plot the residuals in a normal probability plot, okay, we can see that there's a little bit of a heavy tail here, okay, and this would suggest that there probably is a better transformation for the standard deviation. By the way, the observed values were transformed, okay, into ln standard deviation. In this particular example, and the figures here in the ANOVA table were obtained from DAE by Montgomery. Now, if you look at the plot between the factor D and the x-axis shift, which is denoted as factor A, you can see that there is an evident interaction between these two factors. All right. At high level of D, which is supplier 2, it seems to be not very sensitive, but as you can see, if you compare the value of the log standard of the deviation to the point where you have supplier 1 and low x-axis shift, you would have a lower log standard deviation, okay, of the response variable. Okay. Now, if we further look at another graph, okay, a cube representing the average values at different points for y-axis, which is factor B, the x-axis, which is factor A, and tool supplier, which is factor D. Okay, you would see that the lowest deviation is at point where your y-axis is low, your x-axis is low, and you have tool supplier 1. Okay. The last topic is supersaturated designs. Okay, and the motivation for this is basically that you might have many factors, again similarly, no, but the experimenters can only perform very few runs. Okay, so much fewer runs than what we've talked about before. So for here, the fractional factorial design would have the number of design variables k, which is equal to n minus 1, where n is the number of runs, no? And this is usually used for screening experiments. And it is typically analyzed by regression fitting. However, this is not yet used widely, but it can be potentially useful. All right, so that's the end of this unit's. Okay, so far what we covered in this unit include a discussion of the 1/2 fraction of 2 to the k designs, talking about the definitions and principles, design resolution, and then construction and analysis. And as you note, we also still discuss design resolution in the succeeding main topics, including 1/4 and the general 2 to the k minus p fractional factorial design. And of course, under each of 1/2 fraction, 1/4, and the general, we also talk about construction and analysis. Okay, that would include alias structures. And then under general 2 to the k minus p, we also talked about blocking. Okay, and then of course, we also talked about sequential experimentation, projection of designs, and finally, brief discussion on supersaturated designs. And that's it for Unit 2-4. The next lecture will be on regression analysis.